last lab was basically involved stoichiometry in a fairly profound sense because we were doing a solution reaction where we took an ion that was present. Okay, this isn't going to work. So I'm just going to put you down for a little while. Okay, I'll see you in a minute. So we took an ion that was in solution and we precipitated it by adding another ion. And so we sort of did that without really talking about what that means. I mean, what is a solution? What is an ionic compound? We started to talk about what an ionic compound is. We'll get into a little bit more in the next chapter when we actually go heavy duty into bonding. What is the mechanism for covalent bonding? What is the mechanism for ionic bonding? But what we know so far is that we know that, like with an ionic bond, different from a covalent bond, is that we have charges. We have full charges. We have an atom that has either lost or gained an electron and now has a charge. And it is attracted, because opposites attract, to another atom or group of atoms that has an opposite charge. And that's different from covalent compounds because none of the atoms in there actually have a charge. They're sharing electrons. So what we're going to go over today is go in a little more detail about what that actually means. What is a solution? A solution has a very specific meaning. How do you determine the concentration of a solution? When you dissolve an ionic compound into an aqueous solution, what does that actually do? What does that actually mean? And so we're going to go over a lot of that today. And I also wanted to review some more reaction stoichiometry, because that's going to be definitely a big part of test that's coming up at the end of the next chapter, and sort of review how do we determine what a reaction is, what kind of products is it going to make, how do we balance that, and then go over a little bit more what it means to be a limiting reactant, excess reactant, and predicting how much product is made. So all that kind of stuff. So any questions before we get going? Is there any particular one you want to start with, or do you want to just start at the beginning? How would you like to proceed today?
Can we start at the beginning, please?
Always a good place to start, right?
Yeah.
All right, so the first set of questions just has to do with, basically these are like word problems in math. You know, you remember those horrible word problems in mathematics, you know, like two trains moving and you had to figure it all out and solve for X kind of thing. This is similar to that because you're just basically being told, here's a chemical, something's happening to it, give me the reaction. We sort of went over a little bit, I think one of the recitations, it might have been the last one or the one before, where I showed you a trick and how to do these particular reactions. But let's look at the first one. Liquid octane, basically gasoline, is burned. What does that mean? So what kind of reaction is this? Can someone first tell me what kind of reaction this is?
Combustion.
Oh yeah, it is combustion to be sure. Now combustion, what is a combustion reaction?
Something is burned.
Yeah, so something's burned. But when I burn something, that actually has a specific chemical meaning. What does that mean when I burn something?
The heat's flowing out.
It releases heat. Yep.
Oxidized.
Yes, and then oxygen is involved. That's the key. Oxygen, actually those are the two things that are key. Oxygen is required for the reaction. And we'll talk about what oxidation means a little bit later in this chapter, actually. Oxygen is involved, and heat is released. And it's actually the heat being released by that reaction that keeps the reaction going. So that's why You can also think of like, iron rusting. That's also an oxidation reaction, but we don't say it's burning because it's not releasing so much heat that it continues the reaction going at a fast pace, although it's oxidizing just like octane would be here. So, so liquid octane is burned. So what does that mean? So if we were to write that as a chemical equation, that's what we're supposed to do here. What
Thoroughly?
are our reactants?
Is it burned thoroughly?
Completely, yes. So what are our reactants?
Obviously, octane.
Octane is one. And what is the other or others?
Ox
What is it?
Oxygen.
He whispered. Oxygen. In what form?
In gas?
Mm-hmm. But what form of oxygen?
What form of O2?
O2, right. So, and the other thing we have to do is include the states. We have to say what state each of these things is in. So C8H18 is our octane, and it says it's liquid, so we can put an L there. And then plus O2. Remember, O2 is the most stable form of oxygen at room temperature and 1 atmosphere. So if we're doing a reaction under those circumstances, that is the form of oxygen we're going to be using. And so what state is oxygen in at 1 atmosphere and 1 atmosphere of pressure?
Gas.
It's a gas. So we would put G. So in a combustion reaction, what are our products? Oops.
Water.
Water is one. Mm-hmm. Yep. And what's the other one?
Carbon dioxide.
Carbon dioxide. Excellent. I'm going to have to move that arrow a little bit to make room. So a couple things. So we need to put the states of our products. Now, this is a little bit tricky for water. It's not that difficult for CO2. What state would CO2 be in? What physical state?
Gas.
Solid, liquid, gas.
Gas.
Gas. That would be a gas. Now, water at room temperature and 25 degrees, which is room temperature, and 1 atmosphere of pressure, is a liquid. So we would actually put liquid here. Although it's pretty obvious that if we're burning something, the temperature is going to be a lot higher than room temperature, and it's probably going to be a gas. But since we're assuming we're at 25 degrees and 1 atmosphere of pressure, we put liquid for it, okay? This is important for when we do thermochemistry later, when we're talking about the energy of this reaction, because we'll find out that it actually takes more energy to move water liquid to water gas. And we're going to have to account for that energy. But since we're assuming room temperature, 1 atmosphere of pressure, we're going to put liquid there for now, okay? So what's our next step after? So we figured out what our reactants are. We figured out what our products are. What's the next thing we have to do?
Excuse me.
Yes.
When water is in like 0 degrees or 100 degrees, what do we put? Liquid, comma, gas, or just
No,
liquid?
liquid.
Okay.
Yeah. No. I mean, for this, unless you're given the temperature, if you were given a temperature to say liquid octane is burned at 1,000 degrees, then everything would be a gas. And that's actually what happens inside your car. Basically, the fuel is atomized so that it's a mist. So it's basically extremely small molecules, still a liquid, but extremely small molecules. And then everything else is a gas.
Okay.
So what's the next thing we have to do after we figured out what our products and our reactants are?
Balance. Oh,
Yes, we have to balance it. That's exactly right. Beyonce would balance this thing. So in a combustion reaction, I sort of gave you some hints on how to go about doing that. And the first one was balance your carbons first, your hydrogen second, and then your oxygens last. So let's do that. So what's the simplest way to go about balancing our carbons?
Eight.
Where are we going to put 8?
Eight carbon dioxide.
8 carbon dioxides. So that gives us 8 carbons as reactants and 8 carbons in products. Okay, so far so good. So next is hydrogen. Let's balance hydrogen. So how do we balance hydrogen?
9 waters.
Yeah, we'll let somebody else answer for a while. How do we balance the hydrogens?
Nine H2O.
Where do I put 9?
On the product side.
In front of what though?
9 in front of H2O.
Yes, 9 waters. So that gives me a total of 18 hydrogens on the right and 18 hydrogens on the left, so everything else is balanced. And then we leave oxygens for last. And the reason to leave oxygens for last is because oxygen's present in both of the products of the reaction. It's present both. So you really can't balance the oxygens till you've balanced everything else first. So let's look and count the number of oxygens we have on the right. So we've got, what's the total of oxygens on the right side of the equation in our products?
25.
16, 17.
How many?
25.
5.
Where do you get that number from?
9 plus 8 times 2.
So there's, where do we get 9 oxygens, and where do we find 8 times 2? I'm not disagreeing. I would say where do we find them?
9 waters. There's 9 atoms in.
Yeah, there's
No.
9 times 1. That gives us 9. And then here we have 8 times 2. And that gives us 16 for a total of 25. So how are we going to get 25 oxygens on the left side?
You multiply O by 12.5.
Yeah, multiply oxygen by 12.5, or 25 divided by 2. Now, we could just leave it there. If we were actually doing a thermodynamic reaction, we wanted to figure out the energy, and we wanted to figure out the energy burned by, the energy released by burning 1 mole of octane, we would leave it there. But you can't really have, we can have 25 over 2 moles of oxygen. We could easily have 12 and a half moles of oxygen. That's not a problem. But we can't have 12 and a half molecules of oxygen. And when we're writing a reaction, basically we're writing molecules, not moles. We're writing actual number of molecules involved. And so 25 over 2 isn't going to work. So if we want whole numbers on all of our coefficients, how do we address that?
You can multiply it all by 2.
Yeah, multiply everybody by 2. So when I multiply everybody by 2, what do I wind up with?
2, 25, 18, and 16.
Oops. Yeah, so I put a 2. Whoops. There we go. I put a 2 here. This becomes 25. And then this was 18. Right? And this was 16. And then double check and make sure we've got it right. So 16 carbons and 16 carbons. That's cool. 2 times 18 hydrogens, so 36 hydrogens. Let me come over here. 18 times 2 is 36. That's fine. And 50 oxygens. And we have, now remember, oxygen atoms and oxygen molecules are different. So we need to count the atoms, not just the molecules. So we have 18 times 1 over here. So there's 18 oxygens. And then 16 times 2, that's 32 oxygens. And 18 plus 32 is 50. So now we have a balanced reaction and we have all the states. So 2 molecules of octane is oxidized, burned by 25 molecules of oxygen, making 18 molecules of water, 16 molecules of CO2. Yep, there you go. So what would be the next one you'd like to look at? Let's do one of the ionic reactions because there's something I want to introduce, something you haven't seen before. So let's do an aqueous solution of iron 3 nitrate is mixed with an aqueous solution of sodium hydroxide to form a precipitate. Basically the same sort of thing you were doing in the arsenate lab, the arsenate reaction. You added an ion to arsenate, they formed a compound that was not soluble and precipitated. So the first thing we need to do is figure out what are our reactants. And just tell you what the reactants is, but we need to figure out what they are. So how do we write iron 3 nitrate?
Nitrate is NO3 or NO2?
Mm-hmm. NO3, that's right.
NO3. So then Fe.
Okay. Okay, Fe.
And then in parentheses, the polyatomic NO3. I think it's to the -3, right?
-3.
Or just negative. And then the 3 on the outside.
Oh, I see that though. The charge
Yeah,
you mean? Yes. So where does our 3 go on the outside? Up on the top or on the bottom? Subscript or superscript?
Subscript.
Subscript, right. So nitrate has a charge of -1. And iron, we know, has a charge of +3 because it's iron 3. So this balances out. So, and what form, what state is it in? What do we put
AQ.
next to that?
AQ.
AQ, yes. And that means, what does that mean?
It's a solution, so something was dissolved in something else to get FeNO3.
Nope. Means it's in solution. What else does it mean? Means 2 things. 1, it's in solution. What's the second thing it means? So I will agree with you with the AQ. But AQ means something very specific. What does AQ stand for?
Aqueous.
Mm-hmm. So what does that mean?
Dissolve.
Water.
Water, right.
Oh.
It's not just a solution. A solution is something dissolved in something else. The air you're breathing is a solution. It's not an aqueous solution, though, because we're not fish. So just saying it's a solution, it's not sufficient. So AQ specifically means water. And pretty much any time we do solution chemistry, we're talking about water, because particularly with ionic compounds, because ionic compounds really don't dissolve very well in things that aren't aqueous. They'll dissolve slightly in like methanol, and maybe a tiny bit in acetone, but pretty much anything else, like ethanol a little bit, but pretty much anything else, they will not dissolve. So when we say aqueous, we're talking about water.
Why don't we put Wa or H2O on the? Why? Okay, never mind.
Because it comes from Latin, aqua.
Okay.
So that's where it comes from.
Okay.
So that's one of our reactants. What is the other one? Sodium hydroxide.
Sodium hydroxide.
What's sodium hydroxide?
NaO, NaOH.
NaOH, very good. Sodium has a +1 charge, and the hydroxide ion is a -1 charge. And what do we put next to that? What state is NaOH in?
Aqueous.
Also aqueous, yes, because it's in solution. Now that's important for a couple of different reasons. Because we have aqueous around it, if we're given a concentration in solution, it means all of it is dissolved. Okay, so if I say I have a 1.0 molar solution of iron 3 nitrate, it means all of it is in solution. And an ionic compound in solution does what? When I dissolve an ionic compound in solution, it dissolves, it actually goes into solution. What happens to it?
Ionize?
It ionizes, that's right. And that's actually a chemical reaction. Because those ionic bonds are broken and they're replaced with interactions with water. So basically what happens here is that I take my solid iron 3 nitrate, I weigh some out, I put some liquid in a beaker, and then I pour my iron nitrate into it and swirl it around. I might have to heat it to get it all in solution. I swirl it around, but then it all goes into solution. There's no more solids left. So what happens is now I've got this, and I've got 3 moles of this.
Excuse me,
Both in
Fe is 3 plus, right?
Oh, right. Yeah. So that is now in solution, and I have 3 moles of nitrate ion in solution. That's what that means. So if my concentration of iron 3 nitrate is 1 molar, what's the concentration of iron ions in solution?
Can you repeat the question?
If my concentration of iron 3 nitrate, so this whole thing, if my concentration of that is 1 molar in solution, what's my concentration of iron 3? And that's what the square brackets mean, molar concentration. What's my concentration of iron ions in solution?
Isn't it just 1 molar?
Right. Don't overthink it. Yes. If I dissolve 1 mole of iron 3 nitrate in a liter of water, I've got 1 molar iron 3 nitrate. And since it's in solution, it means it all ionizes. Therefore, I must have 1 molar iron. 2, iron 3, iron plus 3. Iron ions have the same concentration. What about nitrate ions? What's my concentration of nitrate ions?
Three molar.
Right, exactly. 3 times as much. Because in the solid, there's 3 molecules of nitrate for every 1 of iron. So there's 3 times as much nitrate in that solid as there is iron. And so when it goes into solution, I get 3 times the number of ions as well. And you can see that in the reaction. I have 1 iron, but I have 3 nitrates. So I would have 3 molar nitrate. That is correct. So let me erase some of this. So what are the interactions I wanted to show you? What gets replaced by the ionic bond? And I'm sort of going a little bit ahead, but I'm sort of showing you what's going to happen a little bit later and why they dissolve. What happens when they go into water is that this ionic bond, which is present, oops, undo. This ionic bond, which is present between the iron and the nitrate, is replaced with bonds between iron and the water. So here's my water, and we'll learn later why it's bent. And it has 2 sides. It has a negative, slightly negative side, which is the oxygen side, and a slightly positive side, which is the hydrogen side. And we use this small symbol delta for being partially charged, not completely charged.
Delta
so-
plus.
And so the slightly negative side of the water interacts with the +3 metal of the iron, and it interacts with a lot of waters. In fact, it would have what we call it would have what we would call a cage around it of like 8 to 12 water molecules completely surrounding it and interacting with it. That's much more stable than those single ionic bonds. And the same thing happens to the negative ions. They interact with the positive side of water. So we have a negative charge here, a slightly positive charge here. They would interact with each other. And so the nitrate ions also have a cage of water around them as well, which stabilizes it. And the same thing happens with sodium hydroxide. The sodium then ionizes to plus, as we know, because it's in group 1, and hydroxide is a negative ion. And the same thing would happen there. Water interacting with the sodium and water interacting with the hydroxide. And those interactions are more stable than the ionic interaction between sodium and hydroxide. That's why it can break, because it's replaced with something even more stable. So this is what we actually have in solution. When I dissolve my iron 3 nitrate and the sodium hydroxide, they're both in solution. So when I put them together, this is what's in solution. Iron 3 ions, nitrate ions, sodium ions, and hydroxide ions, all present in solution. But a reaction takes place. A reaction takes place that forms a precipitate. So there's a precipitation reaction. And we sort of need to figure out what that precipitate would be. So what do you think that precipitate is?
FeOH parenthesis OH3.
So why do you say that?
Because double placement.
No, but why? What makes you think it's? Why wouldn't it be sodium nitrate?
Sodium nitrate is it follows the solubility rule. And
Yeah,
so
we haven't really
anything
got to the solubility rules, but just by using logic at this point, you could figure. Yeah, the solubility rules are actually in the handout that I put on Canvas earlier this week, so you can refer to that. That's you can use that to figure out which. It tells you basically which ions are more or less soluble in water. The other way you can figure, even if you didn't know that, you could figure it out this way. So nitrate, when it's bound to iron, is soluble, right? Has to be, because when we put it into water, it dissolved. So we know that that's soluble. Sodium and hydroxide together are soluble because when I put them into water, they dissolve. So, and we know that sodium is very soluble. So it would be unlikely that nitrate, when bound to iron, is soluble, but when we bind it to sodium, it would not be. That doesn't make any sense. Nitrate because it's so soluble, if we put something with it that's even more soluble, that's not going to precipitate. That doesn't make any sense. And so that's not going to precipitate. So the only thing left, the only pair that could precipitate is the iron and the hydroxide. Those are the only two that haven't come into contact with each other that could possibly precipitate. That's the only one that makes any sense. And so what is our product going to be?
Iron hydroxide.
Yes, but what? That's not enough information.
solid. Solid Fe.
Still not enough information.
And sodium nitrate.
Nope. What's my product?
Product.
What's the product of the reaction? There's a solid product of the reaction. What is it?
Iron 3 hydroxide.
There you go. Iron 3 hydroxide. That's the important thing. It's iron 3 because it's iron 3 is the ion that's present in solution. And so it's going to be iron 3 hydroxide that forms a solid and precipitates. So what is the formula for iron 3 oxide?
Fe parentheses OH and close parentheses 3 subscripts.
And what form is it in?
Solid.
Solid. And remember, we can also put an arrow there to show that it's precipitated. But we don't have 3 moles. We don't have 3 molecules of hydroxide. So that's not, how do we balance our reaction? We need to balance every reaction, right? So how do we balance it?
Put a coefficient of 3 in front of the OH minus and the Na plus.
Yes, both. So it would go here, right? And so therefore we would have 3 moles of sodium ions and 3 moles of hydroxide ions, exactly. So that balances our equation out. Now we have enough hydroxide ions to react with the iron 3 and precipitate. The other question is, what's our other product?
Sodium nitrate.
In fact, no. There is no other product. Can someone explain to me why that is?
Is it because there's common ions at play, so that if you were to reduce it, you just end up with 1 Fe plus 3, which is a
Now,
charge.
interesting, when you say common ions, what does that mean?
Basically, well, I don't really know how to explain it technically, but
They watch the reaction.
Now go ahead with your explanation. So common ions, what?
so they don't really affect Well, yeah, they don't affect the precipitate per se.
Right.
So they're
So
just kind of floating around, and you just throw them out because they're not really that important. Well,
we don't really throw them out, but why they're not a product is
They don't.
because they did not participate in the reaction and nothing happened to them. Because remember, when we were figuring out what all the ions were when they were present at the beginning, before any reaction took place, we had iron ions, iron 3 ions, we had nitrate ions, we had sodium ions, and we had hydroxide ions. We had 4 different ions present. Then there was a reaction between 2 of them. But what happened to the other 2?
Nothing.
Nothing. Nothing happened to the other 2. And so they are not a product because no reaction took place with them. And so we have a special name for those ions. Someone sort of mentioned it before. What do we call those
Spectacle.
ions?
common.
Spectacle.
Spectator.
Oh,
Yeah, spectator ions, because basically they're just sitting on the sidelines watching the reaction take place, but they're not really involved. And that what brings me to question 5, which is the net ionic equation. Now, the net ionic equation basically just eliminates the spectator ions because they're not involved in the reaction. So let's put all the ions that were present at the beginning, which is here. This gives us all the ions that were present at the beginning. So we had 1, 2, 3, 4 ions present at the beginning. And we still have, at the end, we still have that one and that one are still, so they'd be there at the beginning and they'd be there at the end. So we don't include them as products because they're not a product. So if we were to give the net ionic equation of just the ions that were involved in the reaction, what should we write down? We just want to write, so the net ionic equation is just the ions involved in the reaction. No other ions would be present because they're not part of the reaction. So what is our net ionic reaction here? What actually happened in solution to form a product? What are our reactants? What is our product? Well, we know what our product is. Our product is right here. That's the product of the reaction. It's a precipitation reaction. And so a solid was formed and it precipitated. That is our product. What are the reactants?
Iron 3.
Iron 3. And what else?
Hydroxide.
How many? How much?
3.
3. That would be this. That's our second ion involved. 3 moles of hydroxide ions. Because it has to balance. Our net ionic equation has to balance. So what we do these sorts of ionic reactions. We write the whole thing out. And so whatever our solutions are, we write all the ions out for it and the right number of moles or molecules for each one. So that means 3 molecules of nitrate for iron 3 nitrate. And that means 3 molecules of sodium and 3 hydroxides because we had to add 3 moles of sodium hydroxide in the original reaction to get it to balance. And so, but at the end of the day, we still have nitrate ions sitting around and we still have sodium ions sitting around. They're not doing anything. So we could say that now we have sodium nitrate, but we had that before because they were there at the beginning and they're there at the end. So we actually formed sodium nitrate where we just poured the 2 of them together, but there was no reaction. And since there's no reaction, we really can't say that they're products. And so in the net ionic reaction, they're not reactants either, because they were there at the beginning, they were there at the end, and they didn't do anything in the reaction. They didn't catalyze it. They basically just stood back and did nothing.
And watch.
Yeah, they just watched. That's it. So that's what the net ionic reaction means. So I want you to do the other one the same way. Now, the same way we did it here. So if you have a solution of an ionic compound, you immediately know all of it has become ions. So your job is to figure out, well, what ions does it make and how many? Figure out what the product is going to be. That turns into a solid. And then figure out what ions that were there at the beginning are still going to be there at the end. Those are going to be your spectator ions, and you just cross those out to give the net ionic equation. And in the net ionic equation should only be the two ions, that the positive and the negative, that come together and form a insoluble compound and drop out as a solid. So your solid should be the only product. There shouldn't be any other products, no ionic products, okay? All right, that was fun. All right, so who's read through, who wants, what would you like to discuss next?
Can you quickly go over number 2?
Number two. Oh, go back?
Yeah, just so we could know what the product state is.
Oh, okay. So potassium metal, what would be potassium metal? How do we write that?
K.
Just K, single K or K2, or how do we write it?
Just K.
Just K, yeah. It's a metal, so we just say K by itself. And what state is it in?
Solid.
It's a solid, it's a metal. That says solid to me. Plus hydrogen gas. So what's the hydrogen gas? How do we write that?
H2.
H2, H, H3, H4. What do we write down?
H2.
H2. Like this?
No.
No? Okay. Where do we put our 2?
Subscript.
Yeah.
Mm.
And we know it's a gas. So it's a gas. Okay. And then, so it says that the hydrogen becomes an anion. That happens. Not a lot, but it does happen. Especially if you have something like potassium present, because what kind of element is potassium? What group is it in?
First.
First. You remember what they were called?
Alkyne.
Alkali metals. And what do we know about alkali metals? Have we learned anything about alkali metals that might help us here?
You said they were super reactive.
Super reactive, yes. And what form do they take after they react?
Plus 1 plus 1.
Yeah, they're in group 1. So potassium goes to potassium plus. And it can't wait to go to potassium plus. So it goes to potassium plus and releases an electron. And that electron here is going to be transferred to hydrogen. So what are we going to form?
KH.
How many? So is this it, just KH or KH2 or K2H2? What's it going to be?
Just KH.
Just KH. And that's, we can put that, we haven't really dealt with hydrides before, but that's going to be a solid. Okay. Now, how is our equation balanced?
No.
How do we balance the equation?
I think we should balance the hydrogen first.
Okay.
Put a 2 in front of KH.
Okay, I'll put a 2 there.
And
So now
then
my hydrogens are balanced, but my potassiums are not.
2 Ks.
2 potassiums. Right. And so what is this called? What's their product called?
Potassium.
Potassium
Hydride.
what? Hydride. Right. So we use "ide" at the end, and it's hydrogen, so it's hydride. And that's an ionic compound because K is positive and H is negative. And since it's an ionic compound, it's going to be a solid. Okay. So potassium hydride is what you were looking for.
What do we use potassium hydride for?
I have no idea.
Okay.
I don't know what you use potassium hydride for. But that's how you make it. So next question. What would you like to go have a look at?
Let's have a dice.
Someone have a question? What question you want to look at? Or I guess you figured them all out. You're now experts.
4, please.
4. Which one is? Oh man! So we're just going to go one at a time through these.
Yes.
4 you're going to do on your own. But I can get you started. So, what would be the formula for sodium phosphate?
May I speak?
Just let someone else have a chance at it. So sodium phosphate.
NaPO
Uh-huh.
subscript 4, and then
Right. So sodium
3 minus on top.
PO4 where? So where?
Minus 3 upper right. Yeah. Is that it?
Nope.
No, okay.
Because that's not balanced, right? I mean, that is the charge on phosphate. That is correct. But the formula for sodium phosphate is not NaPO4, because in the formula, we don't put the charge in there. We can use the charge to figure out the formula. Why don't we do that? What's the charge on sodium? You got the hard one.
Positive.
Give me the easy
Plus
one.
1.
Plus one. There you go. Right. So that is actually what I'm going to get when I put them in water. And it says aqueous sodium phosphate. So that is what you're going to get when you dissolve them in water. But that is not the formula for sodium phosphate. How do we figure out what the formula for sodium phosphate is?
I'm not sure.
So in an ionic compound, you need to have a balance because it's a compound. It's not an ion. It's an ionic compound. And so a compound has to have no net charge. So the positive, So the positives have to equal the negatives. Our positive charge and the negative charge have to be the same. So how am I going to do that here? Oh, for Christ's sake. How are we going to do that here with sodium phosphate? Think about that. I'll be right back.
Wait, we can do the crisscross thing, right? For this one?
I think.
I don't even, I forgot.
Okay, so crisscross.
Delivery. The dogs always go ape dump when there's a delivery. Okay, so while I was gone yelling at dogs, someone came up with a master stroke to figure out how we're going to balance sodium and phosphate together. How are we going to do that?
We all came to a consensus.
Yes, I love it. I love it. We came to a consensus. Okay, cool. So after much argument and back and forth, what was the consensus?
You just crisscross?
There you go. The old applesauce trick. So after you do that, what's our formula for sodium phosphate? You said the crisscross.
Na3PO4.
There you go. Na3PO4. And so we have 3 positive charges and 3 negative charges and balance each other out. So I need 3 molecules of sodium for every 1 molecule of phosphate to balance it out. And because there's only 1 phosphate, we don't need the parentheses because there's only 1. And we don't include the charges when we're saying what the formula is. So aqueous sodium phosphate, that's what that looks like. And then what's its state again? What physical state is it? What's the physical state of my sodium phosphate?
AQ.
AQ, right. It says aqueous right there. So we know it's not a liquid, not a solid. It's in solution. Oops, aqueous, yes. Now, cobalt chloride. What's the formula for cobalt chloride? Cobalt. Cobalt. Chloride, you got to know by now. Come on, chloride.
Someone in the chat has got it.
Okay, so let me have it.
COCl2.
Right, so cobalt 2, right there, it tells you what the charge is. You don't even need to figure it out. And so cobalt is +2. And we all know that chloride is what charge? When chlorine becomes an ion, what charge does it take on?
Negative.
We know it's negative, but negative what?
1.
Negative 1, because it's in group 7. It only needs 1 electron to get to 8, the happy place. Remember 8, magic number in chemistry. And we'll learn why that is next week. So excited. Right, so if we need to balance the charges, just like any ionic compound means no net charge. So to balance it, we need to have 2 chlorines there. And so we have +2, -2, everybody's happy. And then we also, remember, we put our AQ there. So, because everybody's aqueous, what are my ions in solution? So that's our next step. So as it goes forward, so here's our reaction. So our first reaction, we're actually doing two reactions here. We've already done the first reaction because we dissolved them in water. So that was the first reaction, taking solid sodium phosphate and solid cobalt chloride and dissolving it in water. That's actually a chemical reaction. It's a chemical reaction because you're breaking bonds, you're breaking the ionic bonds, and you're forming other bonds. You're forming the water interactions with the ions. So you're forming bonds as well. That's the definition of a chemical reaction. So what are the ions present in solution when all of these species are present? What's the first ion we can write in there? Are you okay?
Yeah, whether should I talk?
You should let other folks get a chance at answering some of these questions. Yes, I know you're dying to show us your genius, but yeah, just some other people need to get involved. I know you know, but I need to find out if other people know how to do this. So what are our ions that are present? So I dissolve sodium phosphate in water. What do I get?
Sodium ion,
Sodium ion, which is what?
Na plus,
Na plus. How many of them do I get?
3.
3, exactly. So I get that. And what else? What's the other ion I get when I dissolve sodium phosphate? So if I get sodium ion and it's sodium phosphate, what's my other ion?
Phosphate ion,
Phosphate ion. Got to be, right? And what's phosphate ion? What's the charge on phosphate ion?
-3.
-3. There we go. And so when we dissolve cobalt chloride in solution, that completely ionizes because that's what solution means. And what ions do I get from cobalt chloride?
Cobalt ion,
Cobalt ion. Cobalt, which one though? What kind of cobalt ion? Remember, cobalt's a transition metal. It can be a lot of different ions. What is it? What is it this time?
cobalt 2 ion,
Right. So what's the charge on the cobalt then?
+2.
+2, exactly. And I have one ion left. What's the last one?
Chloride.
Chloride ion. And how many chloride ions do I get?
-1.
Oh,
2.
that's the charge. Yes. How many of them do I get?
2.
2. There you go. Right. So now in my solution, I've got 3 moles. I got 3 molecules of sodium. I got 1 phosphate. I've got 1 cobalt, and I've got 2 chloride ions. So let's figure out what our precipitate is going to be. So we have a couple of different options. We know it's not going to be sodium plus phosphate because that's soluble. We know it's not going to be cobalt and chloride because that's soluble. And we pretty much know it's not going to be sodium and chloride, right? Because that's sodium chloride. We know that's super soluble. We make sodium chloride solutions all the time. So that's super, super soluble. What's the only thing left that could precipitate?
Cobalt phosphate.
Yeah, the only 2 left that could possibly precipitate are my phosphate and my cobalt. And when you look and try, if you don't have your list of your solubility rules, one thing to look for is if you have ions with multiple charges on them, they're more likely to precipitate because they're going to form a lot of ionic bonds with each other. There's going to be a lot of charges. When they come together, there's going to be a lot of charge-charge interactions. And so really, really stable compound. And since it's so stable as a solid with those ions being come together, water is not going to get a chance to interfere with those bonds. Water surrounding those ions individually is not nearly as strong as all those charges coming together. And so since you have so many charges coming together, really high charge density, that is going to precipitate because that is stronger than the much weaker water ion interactions. And we'll talk more about water ion interactions in a later chapter. So yes, the answer is cobalt phosphate. What is the formula for cobalt phosphate? That is the thing that precipitates. But what is it? What does it look like? What's its formula?
CO3, PO4 in the parentheses, and then 2.
PO4 parentheses 2. Right, because we do the old crisscross. The 2 goes here, 3 goes there. And we put the metal first. Excellent. We put the non-metal second. And so you can see how much charge there is here. There's +6 and there's -6. That's a lot of charge coming together. That's going to form a really stable compound, which is not going to be terribly soluble. Phosphates are pretty unsoluble in water anyway, because they're so highly charged. You can get sodium phosphate into solution, barely, and you can get potassium phosphate into solution, again, barely. But anything else with any cation, any other like divalent cation, like iron 2 or cobalt or magnesium or calcium, that's going to fall out of solution. That's why calcium phosphate is a big part of your bones, because calcium phosphate is really, really stable. And so it's not going anywhere. It does not dissolve in water. It doesn't dissolve in a lot of dilute acids or bases. It's super, super soluble. So that forms a solid and precipitates. But we have not balanced our equation, have we? How are we going to balance our equation? So that is our product. Yes. What are our reactants? Balanced reactants.
Cool.
Because I only see 1 mole of cobalt and only 1 mole of phosphate. That's not enough to make that product.
Multiply.
Go ahead.
Did you say we should do this on our own?
Yeah, but I mean, we started it. I just want you to, basically, get it balanced. So who can balance it for me? Someone can balance it.
Multiply cobalt 2 ions by 3.
All right, let's do that. So we're going to need 3 moles. Oops. I'm going to need 3 moles of cobalt ions. Yep. And how many moles of phosphate ions am I going to need?
2.
2. Now, how does that relate back to our original up here? These are our reactants, right? So how do I balance my phosphates and cobalt with our original reactants?
You had 2 Na3PO4 and 3 cobalt chloride.
Yep, I put
cobalt
2
2
there.
chlorides.
And put 3 there. Exactly. So that changes the number of moles of sodium ions and chloride ions I have, right? So I'm going to have to change those now. So what do I change those to?
They will both be 6.
Yeah, exactly. They'd both be 6. So at the end, I took 2 moles of sodium phosphate, aqueous, and 3 moles of cobalt 2 chloride, aqueous, and I made 1 mole of cobalt 2 phosphate. And these two were present at the beginning and they're present at the end. So those two are my spectator ions, okay? So do with that information what you will. Okay. All right, so what's the next question people want to have a look at? Since we're just doing these one at a time. I'm not going to do them all, remember. So choose carefully.
Have a dice.
Don't know what that means.
Throw a dice, which number comes to the up, and choose the
I think I'd rather have someone pick one.
Ten.
10, there you go. 10. All right, so another precipitation reaction. Sweet. So what are my, first when you're doing, we've got a reaction, we need to figure out what the reaction is before we can do anything else, right? So what is our reaction here? What are our reactants? So what are the two, we're reacting two things and we're forming a solid product. So what are our two reactants?
Carbonic acid
Okay, we have carbonic acid.
and calcium nitrate.
Calcium what?
Nitrate.
Nitrate. That's this, right? So you don't even need to pretty much give you the whole thing. Now, what are the states here? What are the states of matter? Solid, liquid, gas, aqueous.
Are they both aqueous?
Both aqueous, right. Both aqueous. And what's our product? What's the product that's formed?
Calcium carbonate.
So what's the formula for that?
CaCO3.
CO3, right. And probably you can pretty much figure it out just from the, so we know calcium's +2, and over here, carbonate is with 2 hydrogens. Since it's with 2 hydrogens, each of those are going to be +1, and carbonate then has to be -2 to balance it out. So our product is CaCO3, and that is a solid. So, do we have a balanced reaction here?
No.
Why not?
Wait. Yes.
Yeah, we do. There's 1 mole of carbonate ion, and there's 1 mole of calcium ion. The other 2, again, are going to be spectator ions. So they're not involved in the reaction. So our spectator ions this time are going to be 2 moles, oops,
Excuse me.
2 moles of H plus and 2 moles of nitrate ion. Yes.
So in this case, is carbonic acid completely ionized?
No, but it will be when it reacts with the calcium.
Okay.
Yeah. So we have a balanced reaction. So the question comes down to how much carbonic acid do you need? How much of this is required to make sure all of the calcium here goes into calcium carbonate and precipitates? So we need to figure out how many moles of calcium there are, and then figure out how many moles of carbonate we're going to need, right?
Excuse me.
Yes.
I don't think this reaction can take place, right? Because you also form nitric gas, not gas, nitric acid. Nitric acid can resolve
Yeah, that's
calcium.
that's a little beyond us right now. We're just trying to work out on the problem, if that's okay. Yeah.
Okay.
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 Yes. So we need to balance our moles of calcium and our moles of carbonate. So how are we going to figure out how many moles of calcium there are? What information do we use to determine our moles of calcium? So I need moles of calcium, and then I'm going to balance that with moles of carbonate. How do I figure out number of moles of calcium? What information is there that's going to tell me that? We know it's a 1-to-1 ratio. So if I figure out the number of moles of calcium, then I could figure out the number of moles of carbonate I need. How am I going to figure out moles of calcium though? You have all the information you need right there.
The molarity and the amount you have.
Yeah, concentration times volume equals moles. I mean, that's how it works, because concentration, molar concentration, is in moles per liter. So I multiply moles per liter times liters, and what am I left with? I'm left with moles. And that's the number I want. I want the number of moles. So how many moles of calcium do I have? This is my concentration. That's my molar concentration. This is my volume. That equals moles. Let's not make this more complicated than it needs to be. How many moles of calcium do I have?
Zero 0.0975 moles.
Where'd you get that from?
0.13 molar times
No, not 0.13.
0.130.
Yep. Moles per liter, because that's what that means, times what?
Times 0.750 with an extra 0 liters.
Liters, right. Because there's 1,000 milliliters in a liter. So if we want to figure out how many liters there are from a certain number of milliliters, we divide by 1,000. So when we divide 750 by 1,000, we get 0.7500, because there's 4 significant digits there. So how many moles did you get for that, did you say?
0.0975.
0.0975 moles. Right, so that's how many, since there's 1 mole of calcium, oops, what happened here?
Wrong question.
There we go. Since for every mole of calcium nitrate, I get 1 mole of calcium, that's the amount of calcium I'm going to get from that concentration. So that's how many moles of calcium I need. And we know that there's a 1-to-1 ratio between the calcium ions and carbonate. So how much carbonate am I going to need?
Point 0.0975 moles.
Same number, exactly. Exact same number of moles. So what I need 0.0975 moles of carbonate. So how am I going to get that? That's going to equal the concentration of carbonate, so which is 2.00 moles per liter times some amount of liters. And that's the volume, because it asks you how much 2 molar carbonic acid, basically, since it's a solution and they're asking you how much, they mean volume. Because, you know, it's a liquid. We're not going to measure it in grams or anything. You measure liquids in volumes, in liters, milliliters. So what's the volume required to give me 0.0975 moles of carbonate? Because there's 1 mole of carbonate for every 1 mole of carbonic acid. So we just work out how many liters that is. So how many liters is that?
0.0488.
So 0.01?
488.
488 liters. Right, so we just divide both sides by 2 moles and flip it up, and then what do we get? So we get 0.0488 liters. Right, so how many milliliters is that?
48.8
But
mil.
we multiply it by 1,000 times 1,000 milliliters for every liter. And so we just go 10, 100, 1,000, 48.8 milliliters. And 3 significant digits, right? Because there's 3 significant digits in the concentration of the calcium nitrate. There's 4 significant digits in the volume, but we're stuck with 3 because whatever the lesser number is, 3. Our volume, our concentration of carbonic acid is 3 significant digits. So our volume should also have 3 significant digits. So 48 times 8, 48.8 milliliters. And since I didn't say milliliters, you could leave it as 0.04888 liters because that's a volume that works. Okay. All right, you want to do one more? I figure we do one more, and then I will sort of just keep the meeting going, and you guys can work on them as a group for a while, if you would like. So if we're going to do one more, which one would you like to do? So we've got an excess. So 6 is basically a limiting reactant problem. So you need to figure out what the reaction mechanism is, how many moles of each one are involved, and then figure out which one is in excess. Do you want to do that one, or do you want to work on 7 or 8? 7's pretty straightforward. 8's pretty straightforward too.
Someone has to do 9, please.
Oh, okay. Really? That's just a dilution problem. Okay. So with a dilution problem, we're just taking a concentrated solution and we're just making it more dilute. We're just adding more water to it to reduce its concentration. And so the thing to remember when you do this sort of problem is that there's a certain number of moles in the concentrated solution, and that has to equal the number of moles in your dilute solution. So whatever number of moles you take from the concentrated solution to make the diluted solution, it's the same number of moles, right? All you're doing is changing the volume. You're changing the volume, you're changing the concentration, but the number of moles stays the same. So we start with how many moles are in the dilute bottle, in the dilute solution, and then work backwards to figure out how much of the concentrated solution I would need in order to do that. And so since the moles, what do we know? How do we get moles from volume and concentration? What's the formula for moles? How do we get from concentration and volume to moles?
M times L.
What does that mean?
M times V. Molarity times.
Right, so molarity is the concentration, that's moles per liter, right? Times liters gives moles. Or in other words, the concentration times the volume equals moles. So since my moles here also equals my moles there, the concentration of my first solution times the volume of the first solution has to equal the concentration of my second solution times the volume of my second solution, because the number of moles from 1 is going to equal the number of moles from 2. So that's how you do these sorts of problems. You just take the concentration of the first one times the volume you use, and that's got to equal the concentration of your second solution times the new volume. So that's why your concentration is going to go down, but your volume is going to go up, so it balances out. So let's figure out how many moles of the dilute solution we're going to have. How do we determine that? How many moles of calcium nitrate are in my dilute solution? How do we calculate that? Someone help me. Don't whisper, please.
Okay.
But let someone answer, Raymond. I know you know. So remember, I've got a concentration and I've got a volume. That's enough to tell me how many moles there are. So how many moles of calcium nitrate total are there in the dilute solution? Because it's only the dilute solution we actually have a volume. Because remember, you need a volume and a concentration to determine moles. For the more concentrated solution, what we call the stock solution, and we call it the stock solution because basically in a lab, what you do is you make a solution as concentrated as it can possibly be without it precipitating, and then you just take some of that and pour it out and make more dilute solutions, because it's a pain to have, like, you know, 100-liter jug of a dilute solution when you can just make a 1-liter bottle of a concentrated solution. It takes up less space. And if anyone's worked in a lab, you know that basically space is at a premium because there's junk everywhere. So my dilute solution is the 0.130 molar solution. How am I going to determine how many moles there are? Come on, my 22 participants. I'm just going to start calling on people if that's the way it's going to be. You don't want that. All right, Casey, what do you think?
I'm not sure. I need a little bit of help on this one.
Okay, so to get moles, we take the concentration, which is in, remember, molar concentration is really helpful because it's in moles divided by liters. That's what the capital M stands for. It means moles of calcium nitrate divided by the volume, divided by liters. So if we want to figure out how many moles we have, we just multiply the moles per liter times liters. That's the volume. So basically we're taking the concentration and multiplying it by the volume and getting moles. But remember, the concentration is in moles per liter, so we'll need to multiply that by liters in order for those things to cancel and be left with moles. So this is our volume of the dilute solution, and this is our concentration. So how many moles of calcium nitrate do I have in that solution?
And excuse me, in this case, we don't have to put it in liter, right?
I'm just asking how many moles, I'm just asking the question, how many moles are there in the dilute solution?
Okay.
So how many moles in the dilute solution do we have? We have a volume and we have a concentration. That's all the information we need. Let's just start writing it out. Maybe that will help. So my concentration is 0.130 moles per liter. And I'm going to multiply that by the volume. Now, what's my volume? That's the key. What's the volume of the dilute solution, of the 0.130 molar solution? What's the volume we're going to be using?
750.0 milliliters?
Yeah, there you go. Times 750.0 milliliters. But you see, the problem we have here is that milliliters doesn't cancel with liters, so we can't cancel those units out. So what are we going to do with our milliliters?
Oh, sorry. It's 0.75 liters?
Yeah, we can either do that, or we can just keep going and convert our milliliters to liters. So I want liters, and I want to get rid of milliliters. So I'll put 1,000 here. So now my milliliters will cancel, and my liters will cancel, and I'm left, the only unit that's left is moles. So how many moles is that?
Uh, 97.5 moles.
That seems like an awful lot.
Okay, wait, let me try it again. Zero 0.0975.
That sounds a little more reasonable.
I forgot to divide it.
There you go. You got to divide it by 1,000. Right. So that's how many moles I need. That's how many moles I need to get from the concentrated stock solution. I need to get that many. And so I basically just do that same thing in reverse. Now I have the number of moles and I have my concentration. Now I just need to figure out what the volume is. And so we just sort of basically plug it back into the same equation. But now I know what the moles are. So I have 0.0975 moles. I know I need that many. And that's going to equal my concentration. My concentration is 2, right? It's a 2? No, 0.550, meaning it equals 0.550 moles over liters multiplied by some amount of liters. Now we just solve for the number of liters and we're good to go. So how many liters is that? Might be easier if we sort of put it in a line. So 0.09775 moles equals 0.550 moles over liters times, let's say, X. So basically solve for X.
Did you understand it? Yeah, I got it, but now we're...
So if you're going to solve for X, what do we get for X? Now the easy way to do it, since it's X liters, liters cancels, and all you have to do is divide each side by 0.550 moles. So if I divide this by 0.550 moles, moles cancels out, and I'm left with X equals a certain number of liters.
0.177.
So X is equal to 0.177 liters, right? Because it's a volume we were looking for. So 0.177 liters. Or how many milliliters would that be?
177.
177 mils. Now, an easier way to do it was sort of go back to what I sort of originally showed you, which was because the moles of the dilute solution equal the moles of the concentrated solution. That has to be. The number of moles I take from the concentrated solution are going to be the same. I'm not doing anything with the molecules. I'm just diluting them. So the number of molecules I take from my concentrated solution and then transfer to my dilute solution does not change. The only thing that changes is the amount of water that's there. It just has more water in it. That's it. The number of moles are exactly the same. Therefore, my moles of the dilute would be or equal to the concentration of the dilute solution times the volume of the dilute solution. That's how we calculate moles. And for my concentrated solution, the moles of my concentrated solution are equal to the concentration of my concentrated solution times the volume of my concentrated solution. So all I need to do is plug in my numbers now. So my concentration of my dilute solution is 0.130 molar. The volume of my dilute solution is 0.7500 liters. That is going to be equal to the concentration of my concentrated solution, which I know. So 0.550 molar times whatever volume of my concentrated solution. And I don't know what that is. So that's X liters. Therefore, all I need to do is divide both sides by 0.550 molar. That cancels, and I'm left with liters. Okay?
Excuse me.
That's the simple way to do it. Yes.
So in this case, C the VD to liters, right? Because
can't hear you.
So in this equation, C1 times V1 equals C2 times V2.
Mm-hmm.
We don't have to convert the milliliters to liters, right? Because as long as the units of
as long as your units are the
equals,
same on both sides. That's right.
Yeah. Okay.
Yeah. But if you wanted to go through and calculate the number of moles, since the concentration is in moles per liter, you should have liters. But yeah, strictly speaking, you don't have to have the same. You don't have to have liters as long as you have the same units, but you should have equivalent units on both sides.
Yeah, because this reminds me like the lever principle.
Yeah, distance and force. Mm-hmm. All right, so time for one more question you can ask before I'm just going to stop the recording and let you guys work on these as a group. So do you have any last questions you want to ask? Do you want to just quickly review limiting reagent, excess reagent? Do you remember the meaning of that? Man, I've lost you guys. I'm sorry. So everyone's cool with limiting reactant, excess reactant? The old hat to everybody?
Yes.
It is. Sweet. Okay. All right. So what I'll do is I'll turn off the recording and you guys can keep going if you like. You certainly don't have to stay if you don't want to, but it's kind of good to chat back and forth. You can complain about me and what a terrible teacher I am. You can do all that stuff. I'm not going to listen in. So on Tuesday, we will continue with 3. We'll sort of get into the meat of quantum mechanics, which is fun. I just love it because it just, when you see it open up and it describes the entire periodic table, hopefully something will click for a lot of you. I know it clicked for me when I first sort of looked at it, and it made a lot of sense, and there's a real beauty in it. And then we'll do new lab on Tuesday. I haven't really decided which one yet. I want it to sort of look like sort of the work we're doing, so I'm still working on it. It might not be the one I did last term. I'll let you know. Any questions about any of the, like, recitations you have to turn in, or lab reports, or anything else? We're a little behind at doing the lab reports. I'm almost finished 1 and halfway finished through 2. There's a number of people still haven't submitted 2 yet, so get on that if you can. You only lose like a point a week, but then it starts going up after that.